Hello, I'm Dr. Du-Han Lee. This lecture will focus on how to apply the spectrometry of SOLOS in clinical practice. I believe that this lecture will be very helpful in your clinical practice. Well then, shall we get started? First, I'll briefly tell you why spectrometry is useful in clinical practice. Next, I will explore how to apply the transmission rate of visible light and chromaticity in clinical settings. Our eyes are exposed to a range of light from ultraviolet to near-infrared wavelength. Some of these wavelengths, such as ultraviolet, blue light, and near-infrared, can actually damage our eye tissues and increase eye strain. Using a spectrometer, we can measure how much light from sources like displays, lighting, or even sunlight passes through eyeglasses lenses. This measurement helps us choose lenses that better protect our eye health. While some lenses are designed to block ultraviolet rays or adjust a certain wavelength, a conventional lens meter can't really analyze how well these features work. That's where a spectrometer like SOLOS comes in. SOLOS lets us assess these protective functions in detail. Visible light transmittance is a key indicator that objectively shows the optical performance of spectacle lenses. VLT measures the percentage of visible light that passes through the lens. It's more than just a number. It objectively reflects how we actually see the world through their lens. When optometrists use a spectrometer like SOLOS to measure various lens brands, they can pinpoint the difference between the lens's marketed specifications and its actual performance. Providing this data to consumers or using it as an internal quality control standard can be significantly helpful. Spectrometry is usually used in clinical optometry to check eyeglasses lenses and analyze light sources. But it also opens up some really exciting possibilities in cosmetics. For example, we can use a spectrometer to create lens colors that match someone's personal style. Imagine this. The right tint can totally transform your look by harmonizing with your skin tone and hair color, and it can even express your unique identity. Ideally, a good tint gives you the desired shade while keeping the colors you see natural. By analyzing the spectral data, we can identify any excessive filtering or light transmission at specific wavelengths. This helps us precisely determine the tint the lens will show and allows for highly personalized color tinting prescriptions. Visible light transmittance and visual clarity are closely linked concepts. By using a spectrometer like SOLOS, we can quantify and actually assess how they relate to each other. The higher the VLT, the more light passes through the lens, which generally makes your view brighter and clearer. For people who are especially sensitive to visual changes, even a small drop in VLT can feel noticeably darker and cause discomfort. This is why understanding and measuring VLT is so important for ensuring optimal visual comfort. However, letting in more light doesn't automatically mean sharper vision. If certain wavelengths are absorbed or reflected too much, it can reduce contrast. Our eyes have cone cells in the retina that respond to roughly 3 key wavelengths: red, green, and blue. Most cone cells are sensitive to red and green, with a smaller number tuned to blue. When you perceive the edges of an object, the relative brightness among these 3 wavelengths is really important. So, even if 2 lenses have the similar VLT, the level of contrast can change depending on which wavelength has lower transmission. If you look through the same lenses in a darker environment, you will notice the drop in contrast even more. Because less light is coming through the lens under low light, it's harder to maintain enough contrast for clear vision. So, people who are especially sensitive might feel this difference even more strongly and may complain that they can't see well in dim conditions. However, having a very high VLT isn't always the best option. If more light passes through the lens, the retina's photoreceptors can be overstimulated, making you more prone to glare. This is especially true if a lot of light in the 480 to 600 nanometer range gets through. So, while a high VLT can offer clearer optics, it can also lead to too much light hitting the retina, causing visual discomfort. That's why optometrists need to consider factors like pupil size and visual sensitivity when prescribing lenses with an appropriate VLT. The type of lens material can also affect VLT. Uncoated lenses typically have about a 7 to 15% reflectances, which naturally reduces the amount of light passing through. But in clinical practice, many lenses we use can have a visual light transmittance of over 90%. That's because they have an anti-reflection coating that cuts down on the light reflected off the lens surface, allowing more light to pass through. So, if you opt for a premium AR coating, it becomes much easier to achieve higher clarity. This is something worth considering when prescribing lenses. Too much UV exposure can seriously harm your eyes, affecting various structures all the way from the eyelids and conjunctiva to the cornea, lens, and retina. That's why, whenever possible, we need to rely on spectacle lenses to help protect our eyes from UV rays. Most commonly used lens meters can measure UV transmittance, but they often only provide results for certain parts of the UVA range. To get a truly accurate reading of UVA transmittance, you need to measure across the entire 315 to 380 nanometer range, like SOLOS does. It's also more intuitive to check transmittance values for each wavelength band, rather than just relying on a single number, because it gives you a clearer picture of how the lens is performing. Plus, when measuring UVA transmittance, you should measure at the lens's optical center to reduce errors. If you measure off-axis of the lens, the amount of UV light refracted will be different, increasing the measurement error. Since SOLOS meets all of these conditions, so it can provide very precise results. There are basically two ways to block UV light. One is using a UV coating, and the other involves using UV blocking lens materials. Both methods effectively block UV light, but they perform differently when the lens surface gets scratched. With UV coatings, if the coating starts to peel off because of scratches, the UV blocking effect drops significantly. So, the more scratched the lens is, the worse the UV protection becomes with the coating. In contrast, UV blocking lens materials maintain their UV protection even if the lens surface is scratched. That's why, to ensure consistent UV protection, it's a good idea to use SOLOS to help choose lenses made with UV blocking materials. Light in the 400 to 500 nanometer range is often referred to as a high-energy visible light, or blue light. Some experts argue that this light may cause eye health issues, but more scientific research is needed to confirm those claims. On the other hand, because these wavelengths carry relatively high energy, they can easily scatter in eyeglasses lenses and in the eye's optical system, causing glare and reducing contrast. That's why, rather than focusing right now on how blue light might affect eye health, it's more relevant to discuss its optical effect for improving visual comfort and clarity. It's important to note that lowering blue light can reduce glare and help achieve better optical clarity. So, how much blue light should eyeglass lenses actually block? As the blue light transmittance goes down, you can see on the screen that there's a noticeable reduction in glare. If you look at the transmission graph, the biggest change happens in the 400 to 420 nanometer range. And it's shown here, when you lower the blue light transmittance, glare decreases, which can ease symptoms of eye strain. This makes your eyes feel more comfortable, especially in brighter environments. So what happens if we minimize blue light transmittance as much as possible? The most obvious benefit is that glare can be dramatically reduced. But if you block too much blue light, you may lose some high spatial frequency visual details in bright conditions, making it harder to pick out fine differences. You might also struggle to distinguish light and dark contrast, reducing your sense of depth. On top of that, because the visible spectrum becomes skewed towards the remaining wavelengths, colors can appear more yellowish. That's why, for people who do a lot of graphic or video work, or any task that require precise visual detail, it's better to use lenses with a lower level of blue light filtering. Let's take a look at a case where the blue light transmittance is the same, but the visible light transmittance is different. Even if the blue light transmittance is identical, variations in VLT can affect how comfortable the lenses feel. A higher VLT lets more light through the lens, so things look brighter, but it also makes you more prone to glare, which can lead to eye fatigue. On the other hand, a lower VLT reduces glare more effectively, but everything appears darker, which can lower clarity and color accuracy. With these differences in mind, the examiner needs to consider both the lens's technical features and the patient's environment and preference to provide a personalized lens prescription. The color gamut is the measured range of visible wavelengths within a specific color space that the light sources can produce. CIE 1931 chromaticity diagram represents color using the X and Y variables. X is the relative amount of red, Y is the relative amount of green, and Z would be the relative amount of blue. However, Z is usually omitted because X plus Y plus Z must be equal 1. As a result, once you know X and Y, you can simply calculate Z. Yet, we don't just need these color gamut features to identify colors. We also needed to examine the characteristic of typical tinted spectacle lens colors. From here on, we'll be looking at sample results for representative spectacle lens colors, all measured at a 40% tint concentration. Please note that these measurements can vary depending on the type and amount of dye used, so treat them as a general reference rather than absolute values. Brown or amber tinted lenses can easily help improve visual performance and protect against harmful light. They enhance contrast, reduce glare from blue light, and provide clearer vision, meaning they typically cause the least loss of visual acuity compared to other tints. However, be aware that color perception can change depending on how dark the tint is. These lenses also let more red wavelengths pass through, which can boost the distance perception by highlighting red contrast against bright background. Because these benefits, brown and amber are a great choice for outdoor activities like hiking, skiing, and fishing. Generally, these lenses block a significant amount of shorter wavelengths while allowing more of longer wavelengths to pass through. By reducing the transmission of blue light, they can provide a sharper, brighter view and potentially improve visual reaction time. However, As the blocking rate for short wavelengths increases, color perception may shift towards the longer wavelength range, which can bias color recognition. Despite this, they are commonly recommended for activities like driving, shooting, skiing, and snowboarding. Pink-tinted lenses can help reduce glare and enhance overall visual comfort. It's also known that pink tones may support autonomic balance, helping to promote relaxation and reduce stress responses, which in turn can have a positive impact on psychological well-being. Similar to yellow tints, pink lenses tend to let through more long wavelength light, which can improve perceived depth in your field of view. A light pink tint is less likely to interfere with color recognition, making a good choice for people in professions or sports that rely on color cues. Green lenses transmit less short wavelength light while allowing more green wavelength through, which helps reduce glare and improves both contrast and color accuracy. Compared to other tints, green lenses typically cause less color distortion, so they preserve a more natural color appearance and help reduce eye fatigue. They also soften surrounding light by partially absorbing excess brightness, providing a gentle, more natural view instead of a sharply defined contrast. For people who often experience eye strain or headaches, green lenses can ease discomfort from bright light. That's why they are recommended for outdoor activities, driving, extended digital device use, and for anyone with sensitive eyes. Gray lenses generally don't alter transmittance in the visual spectrum, but they do absorb both UV and infrared light. As a result, there's no color distortion, allowing for a natural perception of colors. They're evenly reducing light transmission in bright conditions. They offer improved depth perception and contrast, making them an excellent choice for outdoor activities. However, in low light environments, the overall decreases in light transmission can diminish visual performance, so caution is advised. Despite this drawback, gray is still one of the most popular choices for everyday wear. Blue-tinted lenses are typically designed to allow more light in the 400 to 500 nanometer range, while cutting down on middle wavelengths. This can lead to bias in color perception, which might not be ideal for jobs that rely on accurate color discrimination. On the other hand, a bit of blue light blocking can help maintain or even slightly enhance contrast. By selectively reducing blue light, these lenses lessen excessive light stimulation, helping to alleviate glare and reduce eye strain. While they offer a unique look that's popular in fashion, their drawbacks such as color distortion, reduced clarity, or decreased brightness can be problematic in work, medical, or sports settings where functionality is a key. So far, we've explored how to use the spectrometer and chromaticity diagram with the Topcon SOLOS. For more information, please visit Topcon Healthcare University. Thank you for watching.